analyzed. So the what video game, it will have a low term frequency, but it will have a high IDF. Inverse document frequency will be high for that. So overall, it will get a high, what I say, high value associated with it. So this is the way how term frequency and inverse document frequency is calculated. If you can see, the log, it takes the distance between them, and as well as FWD is the frequency of the word within the document, and 1 plus, that is, this is the IDF, and FWD is the frequency of the word within a particular document. This is the TF, and multiplying them, we get a matrix. Like for each document, these are the terms are present, and these are their frequencies. So this is the syntactic one. So using TF-IDF, we generate one of the feature matrix for all the documents. Second is that, so here the concept of bag of words come. So each document within the bag of words, these are the words present. The TF-IDF value is this. Base is 2 for log. Is it binary? Yeah, base is 2. No. Base is not 2. It is ln. It should be ln. Base 2 we use for this. Generally, we are taking log of it, not base 10, but here we take it ln. It should not be log actually. I couldn't find it how to write ln, so I slash log, I have written it log. It should be ln actually, base e. So this is our syntactic view. So you can see like it is giving us the information about the words. But what about the association between the words? So to find the association or semantic view, to find the association between the words, we use something called symmetric conditional probability, SCP. What it does is that it gives, like, for a document D, I am having a word, suppose he is. So I want to see if he is present, what is the probability is will appear. And if he is present, then what is the probability he will appear before is. So what SCP does is that it gives a probability association between the two words. So it will give you a matrix of bag of words for bag of words, where each of the column you will have the probabilistic value. So the probability is calculated by this. You can see the conditional probability. If we see PW1 given PW2, and again PW2 given PW1. So if we multiply both of them, we'll come up with this formula: PW1 comma W2 whole square by PW1 into W2. Simple logic. So this is giving me SCP is actually giving me the how the words are associated with each other, and TF-IDF is giving me more information about what words are present and how the documents, which documents are having what kind of words between them. So these are the two different kind of views that we can say. One is that syntactic view we are giving, one is the semantic view we are giving. So this is a typical example where actually we are generating a view from a same documents only. So this is not something we are getting from two different sources. I will give you example later on also where we are using image features. That means two different sources, an image source as well as a text source, to do this search result question. So after extracting these features, we association is only between two words. Yeah, in this case, the association is between two words on. So if we want to know, like if we want to see he is there, so how it will take is that he is there. You know the probability of he is. So you are taking he is as a single word and there as another word. So it is actually not between the two words, but you have to go successively. So it is a change of probability. Like suppose I am calling he is a good boy. So I know he and is. I'm finding the probability between them. Then there is something coming good. Then if you want to find the probability, then he is, you already know. If I have he is, what is the probability I can get good? Or if I get good, what is the probability I can get he is? So you can manipulate it to get the SCP results for entire sentence also. Like how with binary, with single, with n-gram you can get. But in our particular case, we have used it for 1 gram only, not for n-gram. So once these two features are extracted, we feed this feature to our algorithm and we come up with the result. So what we can say is that Moresque, when we have used this particular multi-objective optimization, multi-1 is our algorithm. We see that it is giving a mean and max value. This is AB3 value. F1 score, you can see like it is giving a good F1 score, mean and maximum F1 score. It is giving a good F1. Yeah, sorry. Any? Yeah. Which formula? That one, ACP. ACP, right? Yeah, I'm in 28 number slide. I guess this one. Yeah. Okay. So what it does is that suppose W1 and W2 is there, right? So if I want to find P of W1 given W2, how you write it? P of W1 given W2. We write it P of W1 comma W2 divided by P of W1. Again, if we want to find P of W2 given P of W1, how do we write? P of W1 comma P of W2 by given P of W2. So if you multiply these two, in both the cases you are having W1 and a P of W1 comma W2, right? So that's why it is coming squares, and in the bottom you are getting P of W1 into P of W2. Yeah, is it clear or shall I write it? Okay, yeah. So if you want to do with the n-gram, then you will see like he is there. So he is, you club it. Here you can get the probability of occurring he is together. So he is, you will get it here only. And then comes the other. So chain of probability will multiply it. So, means probability of he given probability given is, the probability of is given he multiplied two again. This whole thing multiplied by them. So you can get it. I guess best thing is taking log of it and then adding them. What people do, they don't go multiplying them, because going on multiplying small number will give you very small number. Rather, people take log of the probabilities and add them, because log of P1 into P2 it will ultimately come as log of P1 plus log of P2. So for n-gram, it is better to go for log and add them. Yeah, so these are the results that we have obtained, and we see like for this SO is actually the such single objective ones. So this is multi-objective problem, multi-objective multi-view. MO class is actually only single multi-objective, and SO is at the single objective problems. So in any of the case, you can see like our algorithm gives a good result. Now we have extended the work of the search result industry. What is, sorry, our hypothesis is that improved clustering can be achieved by defining different objective function over different views of web document and simultaneously optimizing them. So what we did is that, so previously we were saying that you can see like we have taken only the text that is present there, and from the text we have differentiated two different representation and we treated them as a two different views. Now we thought like, okay, why to means divide the text and create two different views. Let's take the images also, as we have the URLs. So we have used those URLs to extract the images from the data set, means from the web pages as well. So now we have actually two different things. One is the visual, that is the images we are having. Another is that web document text we are having. So two different features, image features and text features. So to extract the image features, we use a pre-trained model. You can see the VGG19 model. So now also people use this VGG19. Some others are also there. So what it does is that it takes image as an input, and in the last layer, if you extract the last layer, it will give you a single, like a 1024 or something, a vector size representing that image. So you can say that that vector size you can use as a representation of the image. So we use that VGG19 layers net to generate for each of the images that we have got, to generate a vector from the images. We use this VGG network. And for the textual view, what we did is that last time you can see like we have used SCP. Like both are trivial concept. Then we come up, okay, we have what to make also. So that time we used globe what to make. That was more common. So we use globe vectors. So we thought like instead of going for the SCP, we can take TF-IDF and we have the word vectors also. These are the more efficient way of representing the words rather than the SCP. So we took these two. We took the word to vec and the TF-IDF and we multiplied them to come up with a single textual information. So for the textual view, see how we have done. First, we have generated the TF-IDF. So TF-IDF gives you the distance between for the two different documents. We get some document similarity matrix using the TF-IDF. Okay. By combining that document similarity matrix, we get the TF-IDF. Okay. Now for word embeddings, what you can see, like previously what we are doing, we are having for each of the sentences difference between word to vec and, sorry, I need to see the chat again, sorry. Oh, what to vec is actually, it gives you a vector representation for each of the words. So if you plot them like king and queen, you can literally add them and subtract them based on male and female. So each word is represented by, suppose you can say 300 dimension vectors. So it is more more informative. What TF-IDF does is that TF-IDF only give you the frequency of the word. Suppose is coming 30 times in my document. So its TF is 30. And suppose I am having three different documents where is coming is occurring in all the three documents. So this is my IDF. As because it is coming in all the three documents, I will penalize it. Frequency divided by frequency in all the documents. So the more it will occur, the less value it will have, and we'll multiply it. So TF-IDF will only give you term frequency as well as interverse document frequency. But word vectors will give you a representation of the word, like how well the word, like you can literally add, like if you do king minus male plus female, you will get queen. So it will give you more semantic information about a word. What to make. And if you remember SCP will only give you the conditional probabilities. That okay, he is occurring with his or not. What is the probability of that? Someone else is occurring with some other word or not. What is the probability? It only gives you the probability. But if you want to get insight about the words, that which words are associated with each other or not, that is the word to rank. So now, like you can use the bird. Now the word that you use, they pass it to the word and they take the representation of the word. That gives you the more informative representation of a particular word, right? So, so in this case, once we have the embeddings, so each of the, now you can see, like for each of the words we are having these embeddings, right? Like each of the word is represented by a 300 vectors. So suppose in a sentence, if I have a 3 word, so it will be represented by 3 into 300. And again, in the second sentence, if I am having 4 words, it will be represented by 4 into to 400. Cosine similarity between the words, how they are present. If I want to find the distance between them, then first find the cosine similarity between the two different documents using these word vectors, and ultimately come up with this cosine similarity vector where we are having, okay, document D1 is having document D2 with this similarity. Document D1 is having with document 3 with this similarity. So ultimately, using document similarity and word embeddings, we are generating a document vector, document cross document matrix, where similarity matrix, document plus document similarity matrix. Again, similarity, we are getting a similarity matrix of document cross document using TF-IDF. So we have document cross document TF-IDF, one generated, sorry, another one generated from, okay, just a second. Sorry, yeah, sorry. And another one, we are getting one from TF-IDF, one from source embedding. If we multiply both of them, dot put element wise multiplication. Don't think it's a matrix multiplication. So element wise multiplication will ultimately give you document cross document where both of the informations are there. Okay, so finally we have got our matrix, document cross document matrix, which is having the informations of word embeddings also, TF-IDF also. And secondly, as I have said, like for each of the image we are generating, for the each of the image we have generated the vectors. Similarly, one page may have 2 or 3 images. So combining all those images, we have generated some image vector using document plus document also. So we are having two matrices. One is having word, how the words are associated with one, how the documents are associated similar to each other based on the text feature present in that. In the second case, how the documents are similar to each other based on the images that we have extracted from that. These are the two different views that are representing the different documents. Now we use this information again to run our algorithm. And in this case, you can see, like previously we have only snippets. Now we have also shown like how many web links are active. So how many images we have extracted from them. You can see the average, mean and max image. And here we have used another matrix also. Rather than F1 score, we have used something called FB3 score also. And this is a generalized formula. If you put here 1, you will get F1. If you put here 3, you will get F3, F3, like that way. So once we have it, now we compare our information with, if we take only word to vec, not with the TF-IDF. If we take word to vec along with the TF-IDF, as well as if we take multi-objective clustering and others, and we see like, okay, in again more is given, this one is giving a good results in our case. So these are the representations, like, okay, we are using two different features. Previously for the text only we are using two features. Now we have two different features. What is the advantage of FB3 over F1 score? FB3, these are more hard. Hard means, let me remember it. It like in our information, like in our case, we didn't like all the web pages we didn't need. We wanted to see like only those web pages, like all the web pages were not tagged. What I mean to say, all the web pages that are present in the SRC, those are not tagged. That means out of the 100, if 15 are coming, then we can say, okay, it's a good one. So, but we have to check whether that 15 is matching with this 15 or not. Are you getting my point? I am saying 100 web pages, suppose I am having, so 100 web pages need not to come in my result. Suppose I am getting 15 web pages in the result. The idea is whether those 15s are actually the 15s that are present or not. So this is how it is being checked. A hard checking is done there. So it's not like hundreds are coming, so you're making 100 to 100 and you are getting F1 score. Rather, you have to, out of the choices that you have made, whether those choices are the subset of the elements that are present there or not. Based on that, you have to calculate it. That's why it is AB3, AB1 is like that. It's not like direct matching, like 1, 2, and 3 are coming, 1, 2, and 3 are coming. It's not like that. So obviously we have to remove that also. Like suppose there are 100, but while you are taking only 15 of them, you have to calculate based on the 15 only, not take all the 100, because all the 100 are not relevant. So these information, so that's why FB3 is used in this particular case, FB3. You see the formulas also, it comprises that. What the bar sign and D in the, sorry, yeah, what is the bar sign? Sorry, this one, distance, length of the vector. We have two components now, like whether length or that. Actually, this double bar also represents the length. Yeah, represented it like that. It's not like not in D or not. Some may think like I am saying like D of, except D of I all others. No, not like that. Yeah, norm. Yeah, norm, exactly. Yeah, thanks, Mandar. Yeah, it's a norm. So yeah, using that images, these are the information that we have got. Like while doing our clustering, we could see like 55% of the information we are getting from the text in the clustering, and 44 of the information we are extracting from the images. Similarly, here also we have for different data set, we have this different data. And this is how we have actually calculated, like, okay, this is the agreement index. So we are saying membership matrix we are having. If we run it only on the image part, and then we are taking the total agreement, then we are saying how much image part is uh, contributing to it, how much other part is contributing to it, to calculate this degree of their involvement in this. Actually, that's the formula. So we had the yeah, we published it in, one is ACM and another one is calling. Yeah. So first you can see, like, first we started with the search result clustering, we have taken only the text feature. Second, we have used the same algorithm, but we have only changed, like, instead of taking the same feature from the text, we have improved it. We have taken one feature from the image, another feature from the text. Now third improvement is coming, where we are saying like, okay, now can we improve our algorithm? The same algorithm, if we take these features, how can we improve it? So we use something called generative model. What it does is that uh, the current work proposes a multi-view multi-clustering for the main thing is that generates a single clustering solution by combining the solution in the Pareto optimal form. If you remember in the multi-objective optimization, till now, whatever I said earlier, you remember we get more than one solution, right? More than one solution means you are getting more than one levels, like a solution, set of solutions, two solutions, three solutions you are getting. So when you are getting more than one solution, so while selecting, like which solution you want to select, previously what we did is that we used an external validity index. Like suppose I have used F1 score, FB3 score, and then see whichever of the suppose out of the 5 solutions, whichever solution is giving highest, I have selected that solution as my best solution. But can we come up with some theory where we won't be coming with multiple solutions, but those multiple solutions will be automatically merged intuitively to generate a single solution? So our focus shifted from at the beginning how to make a multi-objective multi-view problem. Then we come to how to represent the data, how to get the data different way. Okay, we solved these two. Now we are again coming to the Pareto optimal form. Like we don't want to use external validity index on each one of them. Suppose I am saying that I am calculating accuracy on each one of them and selecting the best. No, can we combine them and come up with a single solution and see, okay, what is the accuracy on it? So this is where we used a generative model. So the framework is divided into three parts, you can say. The first part uses the multi-view, multi-objective clustering problem that we have shown you to generate the Pareto optimal font till Pareto optimal font. The second case is that we use a generative model. What generative model does is that it takes this Pareto optimal font solution as an input and it tries to generate a probabilistic levels out of it. Once we have these levels, then we apply, instead of taking the best level or best associated with it, we apply a k-means algorithm further on it to generate the final solution. We'll come one by one. So here is my data set. Suppose assume this is my SRC data set. These are the how the views are constructed. In this particular case, we have two views. One is the image, another one is the text. Then is the feature extraction part. From the images and text, we have extracted the features. Then we applied multi-view MOSA, that is our previous code that I have explained. Then we come up with a number of solutions. Suppose n is 3 or 4, whatever you can assume. Our solution is ending till here only. We are selecting best solution out of this. But instead of that, we are passing it through another called generative model. Then in generative model, we are here combining these solutions to come up with a probabilistic solution, then apply k-means algorithm and generating the final output. How we have consolidated the entire thing into a single output. Before coming to this part, I will show you how like this will give you an intuitive idea. Suppose this is my sample one. So suppose I am taking 7 samples. You will get an idea of what do you mean as a solution. Suppose I am taking 7 samples are there. So I am saying that there are 4 solutions generated. You can see this 1, 1, 2, 4, these are actually the tags. That means what? Solution 1 generated 4 clusters. So you can see solution 1 is sample 1 is coming in cluster number 1 here, cluster number 2 here, and cluster number 1 here. So solution 1 have 4 clusters, solution 2 have 4 clusters, solution 3 have 4 clusters, but you see that solution 4 have 3 clusters. So these are my different solutions. When I pass it to the generative model, what it does is that for each of the sample, I will take the maximum. How many solution clusters are there? 4. So 1, 2, 3, 4. These are the number of clusters. These are the number of samples. Once I passed all the solution to this generative model, it will give me a probabilistic value. Like suppose in this value, it is saying sample 1 should belong to cluster 1. Sample 2 should belong to cluster 2. Similarly, sample 3 should belong to somewhere. So anyone can say like, okay, so why don't you take, if it is giving a higher confidence, we can easily select it from here because it is high 0.8, so take 1. So here it is 0.9, so take 1. Here it is 0.72, take 1. Suppose in third case, we are saying, okay, take 4. Instead of doing that, we use this as a feature and we apply k-means on it. So the samples now are represented by this short representation, vector representation, you can say. We apply k-means on it and then we come up with the final solution. Okay, these samples are giving where? There or here, all these 4, where the k value is 4. So please let me know if you didn't understand, or if it is intuitively I could make it clear, like what we are doing actually. Yeah, so for the generative model, what it does is that actually the generative model, what it does, it generates a weak level out of it. So for generating the weak level, it takes 2, 3 informations out of it. What? it takes one of them, like suppose taking all the solutions, it tries to generate a single. First it assumes like, okay, if I apply what a majority voting on it and we come up with a solution, then taking that as a solution, can I see the accuracy for each one of them? So that is one parameter that it takes. Secondly, what it takes is the correlation. So between each of the solution that we have, how the solution are correlated, how much correlated they are. Once we have this information, one is the correlation, one is this accuracy, then they try to analyze this feature. This function they try to analyze, where JW is actually the normalization factor that they have used, and actually the generative model that have used. And then in the WP is actually the weight factor. This weight is actually the learnable weight, the weight that we are learning, the model is learning. And phi t is actually, phi is representing all these things, whether it is accuracy, whether it is correlation, it is written for each one of them. And once we optimize this, once we come up with the optimized weight, it gives you the probability. So given a solution A, given a sample one for this particular cluster one, what is the probability it should come to? What is the probability? So where A is the sample it is giving, one is the cluster it is giving. So ultimately, how this weight or W is regularized, it is shown here. There is a regularization factor W1 is there, and then these bar is actually representing, like, where I am saying that A of I and J given Y of J, that given the cluster one sample, suppose sample one, uh, what is the probability that other samples that given I and not J, that means 1 and 2 others are not there. So compared to that, what is the probability is there? Like probability taking these two, like sample one is coming to, suppose sample one is having the cluster one assigned to cluster one. Condition is that, what is the condition? That it is not assigned to given other clusters. Like sample one is belonging to other clusters. This is a log probability value. Again, you can see log has been used, as you can see, because multiplying the probability value, it will come up with a less number. That's why we always take the log of it and add it. And minus, obviously minus, because it will do it. And finally, arg of it. There should be a gap. Third bracket here. It seems like arg of W minus is something. Yeah. Anyway, this is your weight parameter, and obviously this sigma is also, you can see this is a L1 regularization parameter. So this small epsilon also we are learning from here. So once it's this is a, using SGD we can easily learn this, and once we come up with the formula, and intuitively you can represent it is that, suppose solution 1, solution 2, solution 3, as I have said, like there is y is generated, suppose by taking majority voting of S1, S2, S3. What we try to find out, what is the accuracy, suppose if we take as the main level, suppose, then what is the accuracy with each one of them, and what is the correlation between each of the solution. So pictorially, intuitively, this is how the generative model works, so that it assigns each of the probability to it. Any question, please ask. Yeah, to like to establish the relation between them, like to establish like, okay, the function that we are using, the algorithm we have used, it is really helpful. We have used it on whole range of data set apart from SRC data set. So I will show only SRC one only. Here you can see we have used it on the SRC dataset. So as I've said, like I work in the biomedical domain and also, so my PhD, we have done worked in different like in gene expression, mRNA, in different type of data sets we have used as shown. Like there, yeah, these are applicable. This is good. Okay, these are the results for this experiments only. So you can see there are slight improvement for them. Obviously, the change is not in the algorithm, but rather on combining the solutions, like combining the Pareto optimal solution. So you can't expect like we are getting. Yeah. Can you show pictorial representation of actual examples, say doc1 and doc2? Pictorial picture. You mean to say the pictures of doc1 and doc2? I can show. Then I have to pull it out. Just give me a second. I don't have it here actually. Pardon me. Uh, I need to pull out the paper. Here you can refer the papers. Yeah, if you can see, there are some examples like tattoos were given, then we have given some information about it. Yeah, we have given some images, also sample images, what kind of images we have extracted and how it has helped or not. So these are the images. But the whole data set, I guess I'm afraid currently I'm not having. But you can refer to the paper and you can see it, or you can just uh, it was my PhD work, but I need to check. Then I have to check my drives and all. Google Drive to check the images. So these are the type of images that you get from the uh, web pages. Okay, so you can go through these papers also. You will get more information. Okay, yeah. So these are the results. So this is something you can see, like we have compared also, like suppose if we select the max and mean and selecting within the range, what are the different ABQ measures. Okay, then if we use the k-means at the end and if we don't use the k-means, like suppose I have just told you, right, like instead of applying k-means, we can also do that, assign it to the cluster which is having the highest probability. So if we do that, what kind of comparisons are we getting? And again, there are some, like if you use a generative model, or if you use, that is from the perspective, someone may say like you can join it by using majority voting also, the different solutions. Why didn't you use that? Or these are some other methods of consolidating them. So why don't you use that? So to address those questions, okay, yeah, after this, yeah, I guess it is visible, right? Okay. Mm, now, lastly, till now, whatever I have shown, that is from the clustering perspective, as well as multi-view clustering from multi-objective settings. So, till now, it's from the clustering perspective and all. And this is the last example where we are doing the relation extraction task. So, this is not any clustering task or anything. It is our task is to extract the relations from chemical disease dataset, or yes, a biomedical datasets. And here we have used not clustering but rather classification. We have used deep learning model. And our main contribution in this paper is that the loss function. We come up with the intuitive loss function. So if we go for the chemical disease relationship, like the problem statement is one of the crucial tasks in biomedical domain. If you see, the task is that given a sentence, and suppose there are sentence contains a set of name of chemicals and diseases. Can we associate those chemicals with the diseases? Are they really associated, or they just appear just like that? So that is TF-IDF is used by many researchers. Will you please tell? Okay, just a second. Yeah, like SCP, everybody uses TF-IDF because it's it's very intuitive, readily usable. So nowadays, people don't use TF-IDF, but rather like the SCP that we have used, symmetric conditional probability, that you can get. Or if you like what type of nowadays the best information is that like you can use the word vectors, right? But from this point of view, if you want to use ICP, you can use symmetric conditional probability, TF-IDF, and what else? There might be many. I have to check. If you can check some papers or something, you might get some others. So someone uses like that also. If you parse the dependency parser, like here we have used, not about the word. Suppose the sentences we pass it to the dependency parser and then we come up with the shorter sentences. So these kind of intuitions are also used. These are more called linguistic features. So TF-IDF is not actually a linguistic feature. It is a general thing. You have any word, you just associate with it frequency, the talking frequency. Easy to use, everybody uses it. Previously, obviously, everybody uses it. Now I don't know. Most of the paper may not deal with TF-IDF. It's readily available models, obviously. But yeah, you can see many papers deal with that statistical features also, linguistic features also. If you can take up any paper and see what are the linguistic features they are extracting, that you can use. So here also we have used some linguistic features, not TF-IDs for anything. So like you are using INER or parser, and then you are taking only the, maybe you want to take only the nouns or only the pronouns, or you are taking the nouns and adjectives and removing the gerunds, like that way. These kind of features also people use. These are called linguistic features you can use. That's a very good one. So in this problem, I will show you. Like here also we had used. So here we didn't use TF ideas. Sorry. Here we did. I will show you. So given a sentence, it is required that the relation holds between the most of the topic. Okay, this is one of the example. If you see, I have a sentence: a double-blind crossover study was designed to evaluate the effect of ketamine on spironolactone analgesic in terminal cancer pain patient. Okay, so this is a statement. What is our job? Our job is that within a given sentence, what are the different chemicals are there? What are the different disease name are present? Whether there is a relation or there is no relation, to establish the relation between the chemical name and the disease name. This is the task. The main challenge of this task is that from here only you can see from a single sentence, this is a highly imbalanced problem. You have, maybe you have 4,000 out of 5,000 data, you will have 4,000 no relation data and 1,000 yes relation data. The problem with this kind of this imbalanced problem is that if you run a simple classifier now, it will give you a 90% accuracy, but that is false, because even if it don't learn on the yes relation, even if it learns on the no relation, learns to blindly predicts the no relation comprises 90% of the data, so it will always give you high accuracy. So this is one of the challenge of dealing with these kind of imbalanced data, because the data with less number gets heavily affected, and it is very hard to understand which why, although the accuracy and all is very high. So that's why we don't take accuracy in the imbalance problem. Rather, we will say we will take AUC, RUC curve you take. Okay. What are the challenges? Extraction of the chemical disease from the sentence level is more challenging compared to extraction of relation from abstracts, obviously. So this is one challenge, because taking a single sentence and you want to establish a relation between them, and you are given a whole paragraph out of it, more information you want to take establish a relation between them, that will be more easier. So obviously this is the first case. Then most of the available biomedical tests are imbalanced in nature. I have already mentioned why they are imbalanced in nature, because most of the relations are no relation, only few. In what case data are imbalanced? Data are imbalanced means, suppose there is two tags, right? 0 and 1. Suppose I am saying, you see, 0 and 1. Suppose 1 is my yes relation, 0 is my no relation. If I give you the statistics out here, see, out of 5,713 data, we have 14,722 data as no relation, only 980 data as yes relation, and 11 as the indirect relation. So we have combined them to make it as a one. So not even 1,000. If I just, without doing any plainly, if I just randomly give this data to any classifier, it will give you a 90% accuracy. because it only learns to say no relation. If it learns to say no relation, 472 out of 5713, 472 will come as no relation. So you can see like accuracy is so high, but actually it is a false, right? Because it's imbalance. uh, Table 9. This one is different. We have three different, like training, development, and test. For each of them, you have 500 instances. Okay, so each of them you have 5203 chemical, 4182 disease name, and out of them CIDR relation and CS relation is 1038. These are the instances. So I have told you from one particular sentence you can get, suppose two chemical names are given, you can get four relations, right? Sentence will be one, but your labels will be four, with 000 and then one. So like that, there are 5203 chemicals names are present, maybe unique. 4182 disease name are present that are unique. Out of them, 1032 is actually the relationship that is present between them. So that is used as a training, then development is there, the test set is there. So this is the actually the biocreative 5 data set. So this data set is available. So data set already it comes with this demarcation. This is not something we have prepared, rather they supply it. This is the training set, this is the development set, and this is the test set. And again in the PPI data. So is it clear? Like why? Sorry for the noise. I guess it's clear, right? What I mean by imbalanced data set and why it is a problem. Yeah. Let's get back to the problem. Yeah. Okay. So if you see that most of the available biomedical data sets are imbalanced in nature, I have just shown you. So traditional method, how they tackle the imbalance is that you will find this algorithm. There are many algorithms are present which tackles imbalance. Like how they do, either they undersample the data or they try to oversample the data. That means I suppose I am having 4000 no relation, 1000 yes relation. I will cut the 4000 no relation, I will make it 1000. So I will take 1000 of no relation, 1000. That is undersampling. Or one thing I can do is that I can try to generate synthetic data and add it to it. That there is synthetic minority oversampling. It does that only. It generates a synthetic data for the lower class, means lower ability class, and try to populate it and make it large. And some other methods may be present there. So traditionally, these are the ways how you tackle imbalanced data to make them as per. But these are not suitable due to the presence of large number of duplicate sentences. You can see the main problem in our case is that suppose we want to generate a synthetic data, we want to upsample it, but you see the same sentence is having yes relation or role relation based on the chemical and disease that we are tackling. So obviously, if we try to upsample or downsample, which one to take, which one to means this sentence is same, right? So it causes a problem. So traditional method is not suitable for using that. Also, in our paper, we have compared with that also. So the major contribution of the paper, there's two. One is that the novel multimodal architecture that we have made, and a novel generalized loss function that can tackle the imbalance class. So this is the architecture. Obviously, if someone sees it now, they might say that it's not novel yet, but it was back then. It was a bit novel anyway. So you can see like, okay, for the multimodality purpose, instead of generating something from the text directly, here what we have done is that we have used two CNN. So you see, I will explain what is the shortest dependency path, what is the bag of what I will explain. Like from this sentence, how we are coming to this. Just assume like from the input sentence, we are generating a shorter version of the sentences, and then from there we are creating two different features. One feature by applying three different features. Sorry, one feature by applying CNN and then dense layer, and then coming to the output dense layer, combining them CNN. And another is that we have used a by LSTM RNN network. Then we concatenated them. Then we pass it to the dense layer, and then we generated an output. So what we did is that if we treat all these three, you train them and then you use these only dense layer part as the three different representations. Anyway, uh, so This is the architecture of the individual network. I will tell you, like, what we do it is that first we create this type of setting, train this network, then we remove this output, and then we concatenated all three of the line, and then we passed a multi-layer perceptron, and then we created a final output. So idea is that these these are trained to generate the hidden representations of the data, more intuitive representations of the sentences, these three. So CNN1 and CNN2 differs in the architecture, although both are CNN, but they differs in the architecture. I'll show you. Okay, first is the bag of words feature. What is the bag of words feature? So bag of words includes tokens around both chemical and disease and the verb separating between them. So suppose you are having an example. Suppose W is the window size, then W minus 1 by 2 left and right token are selected for the chemical. I am giving explaining it with an example. Suppose this is a whole sentence. Here 5-HT6 is the chemical name and psychotic disorder is the is actually the disease. Okay. So suppose I am taking a window size of 5. So 5 minus 1 by 2, that means 2. So 2 on the left, 2 on the right. So as because psychotic disorder, nothing have, first take 5-HT6. 5-HT6 don't have anything on the left, that is that and altered, and on the right that is receptors and R. So you can see that altered receptors are. Also we have included involved, because if there is any verb is present between them, we will take them. See, diseases and the verbs appearing between them. So apart from, suppose within this window, there is this verb is not coming involved, but it is actually a verb. So we will not leave the verb, we will take the verb. So between 5-HT6 and psychotic disorder, if their verb is present, whether it is present in the window or not, irrespective of that, we will take that. And again, for the psychotic disorder, we have what? A pathology and off, because on the right side there is nothing. So the whole sentence is represented by this, that altered receptor are involved, pathology disorder. This is bag of word features. Second is the shortage dependency part. So for this, we have used that Engineering parser. So what it does is that you see the tokens. Okay. So what I want to say is that is Myculus and Intimodate. So these are the two tokens. I want to see what is the shortest path between them. You can see after Intimodate, there is something after, there is something reduces, there is something Myculus. So Myculus is there, reduces is there, after is there. You can see there is a relation between them in noun. So we have taken the shortest distance. If there are multiple graph appearing between them, we'll take the shortest graph only. So only these four are related, means these are coming in between them, that's why. So these four are attached with them. Okay. So this is the shortest dependency part, and this is the bag of words. So once you have that, this represent your sentence, entire sentence, instead of representing them are so large. So you can see like this bag of words will make the difference. Even if it is the same sentence, suppose the chemical name is different, then my bag of word will change. Again, if the shortest dependency, if my chemical names or disease name is changed, my shortest dependency path will change. So the entire sentence we will not take, we'll take only those part which are actually relevant to see. So we are generating different sentences out of a single sentence. So the second case counts is that binary cross entropy function. So everybody is aware of, I guess. So this is the loss function that we generally use in a DLL network for a binary case. So whether it's a higher probability or lower probability, but there is only one problem. The problem is that we have imbalanced class. So in one case, it will penalize huge. In other case, it will penalize less. So in both the case, if you see, like if it is a positive one, so our focus will be on the positive one. Always remember, we want to focus on the yes relation part. So even if the yes relation part is uh, not correctly identified, we should penalize it huge. And if suppose no relation part is not correctly identified, we will penalize it, but not that much huge, as because these are imbalance. So we come up with a new formula. What? we are taking alpha 1 and alpha 0. What does is that alpha 1 and alpha 0 are actually the weights. And with that weights, we are taking 1 by P0 to the power log of 1 plus Fn by total positive. So how many total positives are there? What is the false negative? We are multiplying it with this particular parameter. So this particular loss is actually inspired by the focal loss, but focal loss is not like that. But our focus is that if yes relation is getting misclassified, we'll highly penalize it. So that will force the model to learn it, that you learn to identify the misrelation. Is it based on a Laplace transformation? Can be gradient descent will be a solution to find okay, there are two questions. Wait, let me check. Can be gradient will be solution to find the smooth slopes to avoid bipoling. Maybe we use SGD. It is Adam optimizer here we have used to do that. Is it on the Laplace transformation pattern? Not really. If you see the focal loss, so the focal loss was not on the Laplace transform. Focal loss was like the intuition was that the focal loss, that if there is a correct one, it is a less one, but you want to focus on it, and if it is getting misclassified, you will heavily penalize it. But in the focal loss problem, the problem is slightly different. Their loss function is different, not like that. So here we have explicitly included Fn and total positive to ensure. I will show you how we are ensuring it. I will in the next slide only. I will show you like how it is ensuring that we are getting a good result out of it. Can be gradient descent will be the solution to find the smooth slope to avoid bipoling. Only SGD function, I don't think so. Only SGD will give it. Only SGD will not give, because if I use all these simple gradient descent, it will not work. See, when actually SGD is used as an optimizer here also, right? So it will more likely it will learn this, like because its occurrence is huge, its dominant in the dataset is huge. So it is more likely it will learn to predict no relation rather than high relation. The simple GD will not help. Maybe although we haven't like I'm telling you based on the experiments we have done, uh, giving here, but explicitly some other way I haven't checked. Anyway, okay. So coming back to the question, like how it is actually helping, you can see. Like suppose this is my formula, right? 1 plus Fn by total positive. So when very less number of positive classes are misclassified. So positive classes are misclassified. So Fn is tending to 0. In turn, we can say like 1 plus Fn will tends to 0. If Fn tends to 0, so log of 1, it will tends to 0. Under this condition, the loss function is equivalent to the weighted binary cross entropy, right? So if I am making it, if you remember 1 by P over 0, it will give 1. So we will get only alpha 1 and alpha 0. So it is similar to the weighted binary cross entropy function. When it is arriving, when my positive classes are misclassified. In the worst case scenario, like suppose if it is coming positive classes, less number of positive classes are misclassified. In the worst case scenario, when you are getting like the positive classes are not misclassified, like very large number of all the positive classes are misclassified, then the total positive are misclassified as false negative. So we will get something as log of 2, right? So when a positive is having a very low prediction, you see then the probability will be 0.3 and the loss incurred will be 3 times the weighted binary base loss. In the calculation, if you see, it will be approximately around 3 times the total binary loss. And again, if P is 0.9, where P I am saying P is this one. P is actually this one. This one is 0.9 or this one is 0.23. So if it is misclassified, and we are saying that okay, misclassified with what percentage, what probability is there? Because you know in binary cross probability, what happens? Binary cross entropy, we actually assign a probability. It never goes to 1. obviously in max you can say the probability is 0.9 or something. So if it is saying that okay, the probability is around 0.9, so if it is 0.9, then we will say like okay, we are going to this weighted binary loss. What I am saying, in the worst case scenario, all the false positives, all the positive classes are treated as negative. Then you can see the total positive and total false negative will be same. Then we'll have something called log 2. This is log ln 2, 3.1 approx you will get. And based on the what is the probability assigned to them. If a very less probability is assigned to them, then the value will be less. If a very large probability is, sorry, if a very large probability is assigned to them, then the value will be less, and if a very less probability is assigned to them, then the value will be very low. Just let me know if I like if anybody find it difficult to understand. If it is good, if the intuition is clear and this one is clear, I'm moving to the next part. Maybe intuitively, so this is the intuition. When large number of positive classes are misclassified, the loss function focuses more on the most misclassified positive class examples. So that is our intuition. Like if even large number of positive classes are getting misclassified, then they are getting low probability. So we'll get a very high penalty for them. But if they are getting a high probability, but less of them are getting this, then it is equivalent to alpha only. A weighted binary we are following. So based on this, we have applied our algorithm on these data sets. We have used 14 data sets also, and these are the results. We have achieved a good result on it. If I pull this paper out, there are RUC curve, AUC curves is there, which actually, yeah, I guess that's it. These are the references. These are some of the adjusted rank index, what are these, and percentage COA. There's some examples, yeah. Can you please send the related paper with this? Yeah, you can. I see. You can check here. You can go to my Google Scholar. In my Google Scholar, all the papers are present. Okay, I will send it to you. I'm not sure whether it's open or not now, so I can't access it because I don't have access to IEEE. But yeah, this is the paper for the chemical disease. Okay, I don't have access. Maybe from the institution you will have. I don't have access to my own paper right now. Yeah, so this is one. Another to write is this was my first paper. So there are other papers also, like mostly not related explicitly to document classification, but rather than on this. Okay, I guess this is one paper. This is another one. Calling paper already I have posted, so I guess you can see it. Yeah. Any questions? Please let me know. Any questions in the slide? Anything you want to ask? Any confusion? I'm sorry if I failed to clarify any of the doubt. These are like, yeah. So please. Yeah, sure, Pawan. Unmute, okay. I don't know. Uh, do I have the permission to unmute? I don't think so. I guess the coordinator can.
Participants, you may unmute yourself. We have allowed.
Okay, thank you. Thank you.
Yeah.
Thank you, sir. Thank you, Dr. Mitra.
Yeah, thanks.
I'm just looking for one request that I'm also working with bioinformatics field.
Okay.
Yeah, so I just want to know that what would be your expert advice in order to look for the data sets that are available for the biomedical domain. What are the rich sources by which I could get the data sets? And sir, I just want to know that if I'm going to propose some text summarization system for the
Yeah.
clinical tech, what would be the best approach to go for?
Now, if you're going for the text summarization, I don't work in the text summarization part. In
Okay,
the
fine.
company also, I haven't worked, but yeah, I am well aware of it. Like you can see nowadays, the most of the papers are coming on like if you can include the transformer models or BERT models or do some changes on that. Or in my colleagues during my PhD, some of my friends they used to work on the text summarization from multi-objective clustering point of view also and that. But I guess if you are targeting like NLP problem, most of the paper if you see nowadays the reviewers explicitly ask like okay, why don't you like even if you don't include it, the reviewer will ask, okay, why haven't you checked it with this particular model? Maybe there is a BERT text summarization available.
No, dedicated. So you please wait till now,
I
till
guess, yeah.
that.
Oh, yeah.
Okay, one question, sir.
Yeah.
How did you means this relation extraction you have done here? So how are you storing your relations?
One of those relations means whether they are coming or not. Like it will give you binary classification problem type, one or zero.
Yeah, but somewhere you will have to store it, no? Or it is not
Stored.
stored.
No, no. You will give the sentence. How it is represented is that you have the sentence, you have the chemical name, you have the. This is how it will be stored. Suppose this is the sentence in a JSON format. You will have the. This is the main thing. Chemical name,
Okay.
disease name, whether the relation is there or not. So
Whether
these
it
are
is
the
there
identify.
or not. Okay.
Yeah, one or zero. So these are the main the identifying factor. Which chemical you are talking about? The disease you are talking about.
Okay. Thank you. And one more, you have shown that small things you have taken, that is small sentence system you have used
Oh yeah,
somewhere in
here,
some
here,
PPT.
here. This one
Here.
in both the cases, bag of words,
Here.
context dependency. Yeah.
So this red and blue, you have mentioned what is that means why you are
But
focusing on that.
no, no. One is the chemical name, another one is the disease.
But how one will know that it is chemical means
But
it's is that
these are marked. Actually, whenever you will get this data set, these are marked. So the problem is that you know that within the sentence these are the chemical names present, these are the diseases present. So the problem is not identifying which is the chemical and which is the disease. The problem is that
okay.
identifying whether within the sentence this chemical and disease actually have some relation or not. Suppose I am claiming paracetamol can cure fever, so I am making this sentence. So you know I am mentioning paracetamol, I am mentioning fever also. So whether I am telling the right sentence, like whether actually there is any relation between the paracetamol or fever or no, that you have to identify. So that classification that it has to learn. Maybe from the sentences there will be other context also. This is not the context obviously.
Okay.
So that they have to
Yeah.
learn.
Means whether the relation exists between two entities which are mentioned
Exactly.
in your
Yeah. Yeah.
sentence or not.
So
Okay.
entity identification is not the problem. It is already in the dataset and it is already marked. Like these are the entities
Okay.
that are present in the dataset. You have to find out the whether the relation is existing between them or not within the sentence. By reading it, you have to find. So that is the problem.
Okay. Okay, sir. Thank you.
Yeah.
Sir, we
No.
have named entity recognition
Yeah.
in our MTech syllabus.
Yes. Yes.
Natural language processing, we are offering it at a PG level. So in that, in James Allen book, I am referring to it. So
Okay.
in that some entities are mentioned, like the notations. So can you throw some
Yeah.
light on that?
So
Like
see,
the red ball. Suppose we consider the red ball.
yeah.
So then,
The
is there
base
any
thing is
specific?
that, yeah, so base thing is that for any name entity recognition, if you want to check for the name entity recognition, suppose the base that is being used, if you use Stanford NER, online also you will get Stanford NER. And if you want to check like, okay, what is this mean in mod or D object or case or in subject, base thing is that you can check their website. They actually explicitly mentioned like what is the relation between them, like whether it is a subject, whether it is an object, how they're like joined, whether it's referring to it as, whether it is a gerund, whether it is noun or not, like that way. So what was your question? Was it that the question, like what these short forms actually
No,
means?
for
Is it the
expression
question?
of any sentence, is there any notation, specific notation, just to explain it in the literature form? Means when
Specific,
we explain the concept of entity relationship
yeah. Oh,
with
entity and
respect to the
relationship.
text. Yeah, text with respect to text. Means semantic relationship I'm talking about. Semantic
Okay,
roles. Semantic
okay,
relationship.
okay, okay, yeah.
Uh-huh. So like the red ball. So in that James Allen book, it is written ball in bracket, red, comma,
Yeah, I
something.
got it. So they are giving you
Yeah.
the parse tree, right? Actually, that is
Not
all they
always
have
the parse
bracket and
tree.
all.
It is in the not always parse tree, but in the sentence form also. But in this short abbreviation, we can say.
Yes, so generally the third bracket and all, they actually represent the represent the tree type structure actually sometimes. But
Sometimes
I
tree
have,
type structure.
yeah,
Yes, yes.
actually
So that
they represent the tree type
uh,
structure something.
F is bifurcated to NP, means noun phrase
Yeah,
and verb phrase, and then further elaboration is
exactly.
done.
Like from where you are
Yeah.
starting, where to start, and how they are
Yes.
related. Suppose you
Top
are
down approach.
saying
Yeah.
one plus
Top
two.
down tree.
Yeah, suppose I am writing 1 plus 2. So plus will be in between and both of the leaf will be 1 and 2. Kind of
Yes.
like
Yes.
that.
Correct.
But
Uh-huh.
why I have to check because for a long time I
If
have
you
not
can,
used.
sir, if you can share your email ID, so I can share you those screenshots, and then further we can
Okay.
have discussion later on.
Oh, okay,
And
yeah.
another question I wanted to ask, that is, which is the best approach for text? This summarization, or sorry,
Yeah, this.
clustering, sir.
Okay, so like I have used multi-object, so it depends upon like what type of problem you are like you are
Hmm.
tackling. So
Okay.
previously multi-objective optimization were used, but multi-objective you use only when we have multiple conflicting objectives are there. Apart from that,
Okay.
suppose you are telling me like for a data I want to get some intuition about the data. I want to do some clustering over it and get some intuition. So I will suggest like you can go for all the existing like hierarchical or spectral clustering is there. Then
Hmm.
there are spectral clustering. Then there are density based clusterings are obviously there. If you know the number of clusters you need, you can for a basic change like to analyze the data set. For a basic, you can
Hmm.
go for this basic, start with the k-means and all, and then go that
Hmm.
kind of
Hmm.
thing.
Okay. K
Is
means
any
also
base
is
summarization
good
tool
for
available in
some
online?
type of document.
Yeah, k-means also nowadays it not k, it k plus plus means and all. They gives.
K plus plus. Yes.
They gives. These are advanced k-means, so they gives. At least you can get a basic idea of a single
Hmm.
how it is working. Yeah, there is. Someone is asking, but yeah, there is. But BART, BART based summarization model. In the
Okay.
Hugging Face,
Thank you
if
very
you say
much, sir.
BART, BART, okay, that uses BERT encoder and the GPT decoder, BART, BERT. Then T5 model is there, summarization model. You just check Hugging Face, there you can see many summarization models are there. So these are like well known.
Sir, somewhere in your slide you told that one solution can have more than one cluster. Can you
Yeah,
please give any example related with this?
one solution can have more than one cluster. Which one? This one. I got it here, right? This one.
Yes, yes.
Oh, what I am saying is that see, you can come up with 2 or 3. What I have said previously, that generally multi-objective optimization problem returns 1, 2 or 3 solutions, right? 2 or 3 solutions means different cluster types. So suppose one in this particular solution one, you are seeing that 1 and 2 are coming together. What 1 means what? They are coming together. But in solution 2, you are seeing that 1 and 2 are not coming together. Again, in
Okay.
solution 3, so that's what we mean, that they are coming within the same cluster, or they may come in the different cluster.
Okay, sir.
So
Okay.
previously what happened is that, like, if you have 2 or 3 solution, you will run in like external ID, you will check the accuracy with the true level, and then whichever gives the best, you select that one as the best solution. Suppose I am getting, like, out of these 4 solution, 3 is giving me highest accuracy with the true levels that I am having. So I will say, okay, solution 3. So then we come up, like, instead of using the external validity index to check, can we combine these solutions, because different solutions have different objective optimize, can you combine these solutions to come up with a single solution? So then this generative model is applied. So so someone may say, why to use a generative model? We can go for majority voting also. Like for sample one, we can see most of the cases it is going to cluster 1. I will say that, okay, sample 1 is cluster 1. Again, in sample 2, we are seeing all are cluster 2, cluster 1, so cluster 1. Similarly, someone can say that we can go for the majority voting cases. Sample 3, 1, 1. So majority is 1, so it is 1. But and someone may say, like, there are some other approaches how we can combine. So that's why we have compared with this also, like using generative model, how much we are getting. If we use majority voting, what will be the result? If you use some other ensemble techniques, then what will be the result? Apart from majority voting, these are also ensemble techniques. So what will be the result? That's why the comparison is given, like how generative model is helping us. This is the case, yeah. Any further question? Yeah. Any more questions?
Hello, good evening, sir.
Yeah.
Sir, I'm Tanu Gupta and I'm working on question answering system in NLP.
Okay.
Sir, can you give me some idea that how can we decompose any complex sentence? I mean, I'm so confused about it. I have read so many papers, but I'm not getting a visualization about this. That how can we
Okay.
how can we extract? I mean, the contextual part. I want to extract some contextual parts from a long sentence or a complex sentence. How can I do this?
Maybe as of now, I don't have much. I haven't worked on the question answering and all.
Okay.
So maybe I am not the best person to suggest in this. But if you were saying about, like, context-based question answering, where you give a paragraph and then based on the context you want to see do the question answering part, then
Ji.
there are models you can check. Again, there are Hugging Face models at question answering where you pass the context. So what they do is that apparently you can see, like, if you are using attention and then you are using transformers, what they use attentions, right? You can pass the attentions and you can see, like, okay, this is the part that is highlighting, it is giving this part of the question. So it works good when you give the context as well as ask the question based on that. Works fairly good. And but if you want to decompose a complex sentence into a multiple simple sentences, I don't think so. There are sometimes people uses rule based, but this complexity is high.
Yes,
What
sir.
I'm trying to say means decomposing a complex sentence into a small sentences, the complexity is high. Is there any possibility, like, you can train any attention based model to some extent and extract the words on which extract the output of the attention and see, like, which words it is focusing on or where you want to focus?
Hmm. So,
That you can think of. But as of, like, suppose I am saying that I and someone else is going to market,
hmm.
then decomposing it to I am going to market, someone else is going to market. Ideally, it should be like this. So this one, many tried with rule-based type, but rule-based will be pain. After some time, it will be a pain.
Yes, sir.
It will work for some cases, but it will be a pain. But I can't remember as of now any legit model which can actually take a complex sentence and give output as a simple sentences.
Sir, can you
Oh,
please
okay,
tell us
yeah,
any?
Witchcraft.
Sir, can you please tell us any repository of this kind of work, source code repository from where we can start working with this kind of work?
Yeah, you can check with the transformer, right? This is
What, sir?
Hugging Face transformer. If you want to check the models, the best is that wait.
Hello, sir.
Yeah.
Sir, actually, I am a speech. I'm doing my research on speech recognition, and
Okay.
recently I have the QML quantum machine learning. Regarding this, I am now interested to move my research. I mean, to collaborate the research of speech and NLP. So, is there any such way I will be able to do this?
Sir, please
Speech and
send me the
NLP
link.
work. There are many one.
Speech
People work on the speech
speech
recognition.
recognition and NLP.
Yes, speech recognition people do work that I know of.
Okay,
Means there are, but
I am very new to this.
okay, but I have never worked on speech part. Like this is explicitly new for me, but people do work. I have some ideas about speech, but I have never. I don't have any hands-on on speech actually. So
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 how
there
do I
is
start in NLP then?
speech recognition. One of the part is that recognition from the. You can start with simple like from speech to text. Then like if you are explicitly new, then it's the best way to take very trivial problem which is solved by all maybe, and then start with that. So for the speech, there are many things come into play. Your dialect, how you are speaking, in fact the channels that you are using to capture the speech, like whether you are using a 8-bit channel, a
Yes.
16-bit or 64-bit, that will make a huge difference.
Okay. Yes. Okay, sir. So then the first step would be speech to text. Then
Yeah, take up
do
a
some
small
research in the
problem like
speech to
which is
text.
solved by all, then you go step by step. That is easier. Like if you know how to plug in speech, how the speech is working, what are the problems that you are facing, then if you escalate, it will be easier for you. Or if you have any uh, standalone ready problem, maybe that. But I would suggest to do some hands-on on speech and all, then you will get more insight about
Uh-huh.
it. Always
Okay,
working
sir.
will give
Yes.
you a more insight. Anytime.
Yes, sir. Thank you so much, sir.
Okay, so it seems there are no more questions. So I thank Dr. Shantan Mitra for his time and sharing his valuable information and knowledge. And it can be seen that there is huge number of questions being asked and answered in the session. That proves that how the participants was getting interest in this session. So thank you, Dr. Shantan Mitra.
Thank you, Dr. Bhaskar. Thank you, everyone.
So participants, we will take 15 minutes, 10 minutes break, and at 6:15 we will start again.
Okay, sir.
Excuse me, sir.
Yeah.
Sir, today we have that test, no? 7:45.
Yeah, we have the test today.
So before that, the session would end, no? Lab session.
Actually, it is a request to all participants that be present, attend the next lab session. We will wrap up the lab session at around 7:45, and from 7:45 that link of the quiz will be active. And the quiz will be on Google through Google Forms only.
Google Form
The
only,
way
no?
you
No,
have
because
registered
Canvas we
yourself.
are not still getting the invitation, sir.
So that's why we have stopped getting sending invitation through Canvas. We will shift all the
Yes,
materials to Google because a lot
yes,
of
thank you.
complaints and lot of participants are still able to receive that. So
Yes,
that's why
yes.
today we have
Thank you.
decided that everything, all these lectures, etc., whatever is there in the Canvas, it will be remaining there. Other things, the videos and other lectures, we will shift or we will copy and paste everything in Google Drive, and that link will be shared to you.
Yes,
Okay,
thank you very
and
much.
all the quizzes will be through Google Forms. So make sure that you are starting your quiz at around 7:45, and the quiz will end at 8:05. We will stop the link at 8:05. So it is a 20 minute. There are 20 questions. 20 minutes will be given.
Sir, sir, the link will send by WhatsApp, no?
No. You have to just answer in that Google form the way you have filled the form for register yourself in this course. So there the options will be shown to you. You have to select the correct answer, all the questions and submit button. That's all.
No,
You
sir.
do not need
Where
to.
the link? By which? Where
That's a
the link will?
link. That link we have already sent in the morning through WhatsApp. I think Bhaskar we have already sent.
Yes. We have sent it in the
It is
WhatsApp group
there
as
in the
well as
WhatsApp group.
Even in the chat window also we will share that. So we are taking all outlets. Even in Canvas also we'll paste that link. So we are pasting it at all outlets so that you can get access to it.
Okay, sir. Thank you.
Even if someone is not getting, it is a request to all the participants. If some of your friends are not getting, you forward the link, whatever you have got. And while you are answering that, your email ID will be recorded, so there is no problem. So you just forward it if your friend is not getting, so you can forward that link to them also. But make sure timing is from 7:45 to 8:05.
Sir,
Okay?
yes, sir. One question, that is yesterday's session. Can we get that recording?
Yes. Recording. I have not downloaded it. I am downloading it. So yesterday's and tomorrow's both. First 2 days lectures are already shared. Video lectures through Google link. Yesterday's and tomorrow's
Those
that too will be
lectures
shared.
are today. Those are shared because I did not get.
No, I think we have shared it tomorrow. Yesterday itself, and I have shared the link through WhatsApp. Again, I will send the link. Okay.
Yeah, because I did not get first 2 days also.
Those links are already shared.
Location
I
I
will
want.
again resend that link.
Okay, sir. Thank you.
Okay. Okay. Thank you. Then see you at 6:15.
Excuse me, sir.
Yes.
Sir, actually, I'm trying to join the WhatsApp group, but it is showing like group is full, so I cannot join it. I'm trying from the
Don't
first
worry.
time.
Every information we will also paste in this chat window.
Yes, I also didn't. I'm not getting that
I
WhatsApp
think
group.
there is some limitation in that. WhatsApp. No, around 250 participants they are allowing
57
only in one
participants,
group.
sir. Yes.
Or that
We
drive
have
which you
already.
shared on the first day, sir, if the material or anything is shared in that drive, then we will get everything from one point. So is it
Yes, I
possible?
will put everything in single point. Don't worry. That's why we are stopping Canvas right now. We are not going anything through doing anything through Canvas. So those who have not received any Canvas link, they do not need to worry. Those who have already received all those materials which I can share, I will share there also so that it will remain there for a long time and you can see it in at any time. Okay.
Okay, sir.
Thank you, sir.
Thank you.
Okay, so you can start now.
Yes, sir.
Okay. So what is my plan? And on last day we had stopped due to time limitation. So today in fast forward manner, what we had left that day, I will just cover them and then we will go for word embedding. Okay, because this part is also important to go forward with embedding and other things. Okay, so today I am not going to type the code. Mostly I will do copy and I will just explain the code to you. Okay, and if you just want to get access to the code, just a minute. Yeah. So here is the link I'm pasting in the chat box. Let me see. Okay, you go to this link and you will find a notebook there, a notebook file. You click on that and it will be open in GitHub, right? So it will be displayed and you can just take your code from there. What is going on? How somebody else is doing this? Okay, I think now it is okay. Okay. So I had pasted the link here. You can just go through which file to download. Okay, let me show you. This is the file name, or I can just now you click on this, it will directly open the file name. Okay, so first thing what we want to do is tokenization. So the same sentence we had used in the previous session. I am going to take that one as example. Okay, so for tokenization, we have to first download this package called Pound. So just download it. Then there is two kind of tokenization. One is called sentence tokenization. Another is called word tokenization. So what happens if you have a big amount of text, like a essay or news or article. So in that there will be numbers of sentences. So many times we may need to split the text into sentences. Okay, so this is what the first function is: sent underscore tokenize. So you can see from NLTK, we're importing this sent underscore tokenize function, and we are passing text. Okay, so it will just give us, split it into sentences. You can see, this is a sentence. So every sentence is split into, or kept into in this double quotes. Okay, this is another sentence. This is again split into another sentence. Okay, and so on. So this is how it gives you back this function returns these sentences. Next is we want to split into word. So for this, here we are writing a function for our future use. Okay, and function name we have kept here tokenization. Okay, so what we need to do this word tokenize is the function function which is available in nltk.tokenize. Okay, so we call this word tokenize, and this function, my tokenization function, this name is given by us, which will return the words or tokens from each sentence we will pass to it. All right, so this is the thing. So if I run this, you can see here I'm sending the text. Okay, so what is going to happen? It is returning all the tokens available here. All right, so next thing, even we can take some good text or clean text if we have previously, that will look better. So stop remove. Okay, so this is not text. New text, I think we had new text, right? Previously we had done it. But our new texts are also not in good. Yeah, this is a good one. So I just run this once, and I take this new text and pass it to the tokenizer, so that some clean text we can pass to the tokenizer, and you can see how it is doing it. Okay, so yeah. Okay, so these are the tokens we have in our text. Okay, next thing what we are going to do, we want to just say the words into it. So using text bulb option, we can see it. So there are actually different use of text ball. We will show later. Okay, I'm not going into detail of it because we will find for spell correction this text ball will help us. Okay, so if I just move forward with spelling correction, so I have written a function called spell correction. What we are sending here sentence, okay, and see from text block, we are importing this text block, okay. In sentence equal to text block, we are sending sentence dot correct. So it is having a function called correct. What it will do, if there is some misspelled word in the sentence, it will correct it. Okay, and after doing the correction, it will store it in the sentence and return the sentence. Okay, so let's pass this new text. Okay, so you can see, some of the, there is almost wrong misspelled thing. Okay, so yeah, this is what it does. Okay, next come to the most important thing, and one of the most important thing in NLP, that is called stemming and lemmatization. They are basically different thing. Okay, both are used to reduce any word to its root form, but there is different technique they follow. If it is a stemming method, it is basically based on some kind of reducing method. That means it is having some algorithm based thing that okay, ing is there, remove ing from the end, or if there is a set of defined prefix and postfix which we use to add to the word, to any word, to change its form, like change a verb to present tense to past tense. Okay, so if we do that, yeah, so stemming basically does based on algorithm. Okay, there is some step to perform and it give you the result. Now, what happens with stemming? The result may not be a real word or dictionary word. Okay, but with lemmatization, as it follows uses a dictionary with it. Okay, so always the result of a lemmatization is a real dictionary word. Okay, so this is the thing. Now, let's take some example for this. See, so there are two things we are importing here. You can see one is Porter stemmer, another is Lancaster stemmer. So there is two stemmer. Okay, so what these two things will do? They will do stem. Okay, so both the you can see how both the Porter stemmer and Lancaster's stemmer functions. If I run it, we have passed here. See what? Cats. Okay, and to the Lancaster stemmer also you have passed cat.
आप इस बात को नोट कर लीजिएगा। मेरा बड़ा भाई का जिस दिन शादी होगा उस दिन कल्लू बिहार में कदम रखेगा।
Okay, so you can see here in both the cases, cats was passed and it is returning cat. So yes, it is just a remove, but trouble was passed to this Porter stemmer. So what it is returning, TROUBL, E is removed. So you can see this is no more a dictionary word, right? So this is what happens with stemmer. Okay. So there is another example. If I do stemming of our tokens, what tokens we have or words we have. Okay, so what we will get, you can see here, URFLI, it is, you can see it was flying, right? Say it, now you can see as I have applied stemming, the result is not a dictionary word anymore. And so on, we will find lots of example, things happen to this. Okay, then come to lemmatization. Okay, so the same thing, what will happen if we use lemmatization to our tokens. So for using lemmatization, you can see what we are doing. We are just downloading WordNet dictionary, right? So we are first downloading what? WordNet. And this. Okay. Now, from text valve, we are importing word. Next, what we are doing? Lemmatization function I am writing here. What we will pass? Sentence. Now words equal to sentence are split, so sentence will be split into word. Then lemmas, each sentence will be split. Again give us lemmas for each word in the sentence. So I'm taking an empty list, and that is called lemmas. So for word in words, it is just lemma dot append word. This word is this word. This capital W. You can see here. Okay, don't confuse with this. Or better, I write here only W so that you will not get confused with these two words. Okay, password here. Okay, pass W here. Okay, so if I run this, you see what change you are getting. Okay, so there is something. Name W is not defined. All right. Sorry, something I have. Yeah, there is a mistake. Yeah. Or oh shit. Better I do here. Sorry, words. Right now for W in words. Now it is okay. Okay, so these are the things. Let add here print. Now, if you see what happened, this flying remained flying. It in case of stemming, it was converted to FLI, which was not giving any meaning. Okay, which was basically not a dictionary word. Okay, but here it is becoming, it remains flying. So many of us may have question that then why stemming is there when lemmatization always gives dictionary words. Reason is that when you are using neural networks or deep learning models for we are doing what to make and all these things, then only this symbol matters. Okay, if it is FLI for all the sentences, that it is basically substitution applying by FLI. So it can happen. Okay. So that is one thing. There is no big deal of using stemming over lemmatization or that. But another thing is there. As lemmatization uses dictionary, it always searches things in the dictionary, so it gets slower than doing stemming. Okay. So okay, let's move forward. Who said this? Okay, there is a question in the chat box. Without W defined, how are you getting answer? Who said I'm not using defined W's? You can see here for W in words. So this is how we write for loop, and for this, this W need not to be defined. You know, in Python, if we write for loops, we can have a variable here which will automatically defined and initiated, to and some null value. Okay, so this is what happens in Python. So W is a, you can say, iterator for the for loop. So we don't need to define it. All right. So previously, by mistake, I had written W here. So it was searching, where is this W? Because this is supposed to be a list, right? So that was the reason we had that error. I think I made your doubt clear. Okay. Next, POS tagging. Yesterday, there was lots of discussion on POS. Okay. So again, we need this pang to be downloaded. We have already downloaded, so I'm just removing it. Okay. And NLTK download what? Average punctuation tagger. Okay, this is another tool available in NLTK. So we need to download this because we have not downloaded previously. Okay, so it is downloaded to the system. Now we don't need here we write what? New text, right? Okay, new text. So if I run this, you can say it is tagging all my parts of species, or you can say all the words in my sentence. U is a pronoun, R is a verb, or you can say BP means the actual B verb. Okay, flying is a verb, and so on. You can see. Okay. Next thing is called chunking. So what is chunking? Chunking is you can see when you have done this POS tagging, it is simply tagged each word, right? But we always like when we use English language, work on English language or any other language, we like to see them as per the grammar, or there are phrases basically, and we can define phrases like say the cat. So there is no reason to always calculate the and cat separately. We can treat them in a single phrase, right? So that is called a noun phrase. So chunking basically helps you to do that. Okay, so just take this. Okay, so I don't need this. NLTK tokenize. So, new text. Okay, so print tokens. So we will have the tokens here first. Then we are going to tag the tokens. NLTK.post tag. Post tag is the function which tag your tokens. Now we are just defining a noun phrase. How? Some determiner dt. Okay, that is the a and the all this thing. Okay, and then some I'm forgetting JJ, and n for is noun. Okay, so if you see, oh, so draw will not work here basically. If you are using your local computer, this part will work. Otherwise, this draw will not work. Okay, so let's inactive this one. Okay, so you can see here, you are flying. All these things are done by this tags. It is print the tags here. Okay, then yeah, you can see these things are coming into this manner. S means sentence. Basically, here you are seeing it in this form, but it is supposed to be displayed in in a tree form, so that you will understand different phrases into it. Okay, so I'm not giving much time onto this. Let's move to more important thing for today. Okay, so there is some other chunker. I'm not going to those things. Okay, yeah, this is something important. I was telling you that this text bulb is basically having many important functions. So this is another function called n-grams. I think many of you know what is n-gram. Okay, so when we do context analysis of what? Of any text, right? So what becomes important is your words are coming with what other words with it, right? So based on that, we define the context, right? So you can say that this person is as good as snake. So good and snake is coming together. So you can understand as will be removed by when you will do cleaning. So good and snake will come together. So how the context will be defined? When you will do this, you can see all the two words, consecutive words are combined together. Okay, so it is called n-gram. So this n defines this number 2. Okay, if you put here 3, it will give you 3 gram. Okay, you can see this. Okay, so based on this, your learner, your model can learn that in what sequence in your document the words are appearing. Okay, so the relation between different words it can learn. Next thing is that most important thing you are studying from last few days is this one. Sorry. That is this bag of word and TF-IDF, right? So here is an example you can see. So we have 3 reviews. Okay, this movie is very scary and long. This movie is not scary and is slow. This movie is spooky and good, right? So these are the 3 different review short sentences we have. Now, first of all, what we have to do, we have to create our vocabulary, which is basically the function of bag of word, right? That means how we do this, generate this vocabulary, we need to find out what are the unique words are there. Okay, so based on these 3 sentences, here are the unique words we found. Okay, and we just do, give me 1 minute, please. Okay, sorry for the disturbance. Yeah, so next what we do, review 1 is the corresponding to the review 1, review 2, and review 3, and we have all the unique words available there, and we just do present absent. Okay, by putting 1 for present, 0 for absent. Okay, we just do this, and we just by doing this we can represent our sentences. So you can see, I can read the sentence instead of from here. You can read it from here. This movie is very scary and long, right? Next, review 2. Okay, this is a mistake here. It will not be 2. It will be 1. Okay, so you can see here. I can read the second sentence from here also. This movie is and should be absent here. Okay, long should be absent. So that there is some mismatch with this. Slow should be present. Okay, so this, okay, 2 times is there. So yeah, it will be 2 times. Sorry. Okay, so yeah, so let's see here. Okay, this movie is then not should be present here. Okay, so okay, so there is some mismatch in this. By the way, you can understand that what I mean here. Just simply absent present, and again, if some word is appearing 2 times in a sentence, that is going to be counted, and that is that number of presence of each word in a sentence is going to be considered here. All right. So let's do this, simple mathematics using Python. Okay. So this is the part of doing the vectorization of simple vectorization of the sentence. Okay. Next, what we will do is calculating the term frequency inverse document frequency. Okay. So first thing is term frequency TF. How do we calculate it? Count the term T in the document. Okay. Total how many number of time a term is appearing. Term means here a word. Okay, is appearing in a particular document. Okay. So here in our case, one review is one document. Sorry. Okay. So one review is one document. Okay. By number of terms in the document. How many terms are there in the document? So in the first document, there are 7 terms, right? So here it will be 7 for the first document. Okay. So for example, TF movie, it is going to give you 1/8 as a TF. Okay. For second document, if there is total 8 number of word and movie is appearing 1 time. Okay. So it is going to give you 1/8. So like that. Okay. And in the second document, a second review is appearing 2 times. So it is 2/8. So I think you got to understand what is term frequency. Then document frequency, we calculate. That means in the DF is the number of total occurrence of the term T in the document set N. That means how many times a term is appearing in all number of documents. A movie, DF of the movie will be 3 because we have 3 documents and all 3 movie is appearing 1 time. Okay, so DF of 3 will be DF of movie will be 3. But if it is DF of is, it becomes 4 because it is 1, 2, 3, 4. It is 4 times, right? So in the same way, there is inverse document frequency. So what is inverse document frequency? It is log of total number of document, in our case it is 3, by document frequency, DF. All right. So say for movie, we know that DF for movie is 3. We have total number of document is 3. So it is IDF of movie will be log 3/3 equal to 0. Understand? Clear? Next comes TF IDF. TF IDF is simply multiplication of TF with IDF. Okay, this is IDF. Okay, so simply we can multiply and we can calculate. Okay, now let's move for the coding part. Okay, so okay, so we are creating our corpus. Here you can see review 1, review 2, and review 3 we have. Okay, and we have put them in a list. So this corpus becomes simply a list of 4 documents. Understand? Then what we need to do, we will just do some pre-processing. Good thing is that we already have written all the functions for doing this pre-processing part, right? So what we will do, we will just call these functions where we just first tokenizing all the input, then we are converting to the lowercase, then we are doing removing the stop word, then we are removing the punctuation. Okay, if we run this, you can see convert to lowercase is not defined. Okay, so we have this function here. Okay, so this function name is, I think, changed there. Sure. Okay. Again, stop word, remove stop words. Let's see, I think again that function name is not matching, not matching with the function name we had defined. So remove stop word. Now count, this count stop word, then removing stop word. Okay, so okay, so we don't have this function here. I think I have written here. That is the reason I am calling this. So let's take this function from there. Yeah, it is here. Stop words not defined. So it is stop words. Let me see once. Give me 1 minute, please. Stop eng we had defined here. So where is stop words? Here. All right. So my function is ready. So let's see. Yeah. So you can say after doing on all these preprocessing, you can in the first sentence we have only 3 words or tokens. For the second sentence also, movie, scary and slow are there, and the third one, movie, spooky and good. All these, these are the words are there in our hand. Okay, so this is the first thing we need to do. Next, we will go for we will go for doing the bag of word operation. That means we will do, yeah, we need to find out the unique vocabulary from there. Then only we can generate that table and do this present absent thing. Okay, so okay, we have just we need this output in a variable, right? Okay. Yeah. So preprocessed is a variable in which this processed, these values are corpus is stored. So just finding out the unique values into it, or unique words into this, right? So you know what is set? Set is a collection of terms or collection of symbols, whatever you want to say, and they are basically unique, right? In set, no element repeats. So we simply, I'm doing set of making a set using all these terms available. Okay, so if we do that, it basically it will remove all the terms which are coming common. Okay, our unique terms will be kept here. Okay, so using this set, we can do this. Then we need to create the vocabulary, right? So let's create the vocabulary. So you can see what we are doing here. I just I have just written a list as variable name, so that we can understand what kind of input we need to give to this function. Okay, then we are creating an empty list. Okay, then count. We have taken a counter and it is initiated to 0. When this counter is less than length of this list of list. So how many times it will iterate this loop, while loop? It will iterate basically for the each word in the list of list. Okay, or each element in the list of list. Okay, and what are the element here? In the list of list, the elements will be like another list. Okay, so this is the example of list of list. You can see. Okay, you can see this extra brackets. This is a list, and these are the small list inside it. Okay, this is list of list. So the while loop will give us a track on first list, second list, and so on. Okay, and now in the first list, for I in the list of list counter, okay, if I in list new, initially our list new is empty, right? Then continue. Otherwise, we append. So why we are doing this? This is for again creating the vocabulary. The same. This is one way to doing it. This is another way to doing it. Okay. So you can say why this two way you are showing. Reason is that if you want to maintain the sequence of the word, in what sequence they have been appeared in the original documents, then you can follow the second method. Okay. And if you don't care about the sequence, then you can simply take the set. Okay. So you will find in the inbuilt functions in NLTK, most of them, many of them don't care about the sequence. They will give output like this. Okay. But if sometimes, for a small data set, it becomes important, you can go with this. Okay. So this is one thing. Now, how we can calculate the term frequency? Did you remember? I had told you the formula for term frequency. You can go back and you can see it is count of a term in document and number of terms in the document, right? So here we are doing this for each term, and we are creating empty dictionary, and in this we will calculate the term frequency. Okay. So this is appearing 3 times in all the document. Movie is 3 times and so on. Okay. So this is term frequency. We have calculated. Okay. So these are not term frequency. These are number of times they are appeared. All right. And these are the term frequency. Okay. For movie it is this and so on. Okay. So total number of word, this term, this 3 is divided by total number of words in all the documents. Okay, so this value is coming this small. Understand? 3 documents we have, say 7 plus 8 plus 7, almost 15, 22 number of words are there. So it is going to be term frequency of this is 3 by 22, which is like this. Okay, so this is the way how we can manually calculate the term frequency. Then inverse document frequency. I have already told you how to calculate inverse document frequency manually in pen and paper. Now here we can see we are sending the corpus and we are sending the vocabulary, right? So that in the vocabulary we can check that we can check that there is words which are available in the vocabulary and how many times they are appearing in the corpus and how many documents are there. Okay, so you can see the corpus, there are 3 items. You know this, right? So N is taking the length of corpus, right? So that you can understand how many capital N I have already defined here, right? Capital N is what? See, number of document is capital N. So simply this capital N is the length of corpus, which will give you 3. Okay. Then we are taking a for loop, I in vocab. That means for each word in the vocabulary, count equal to 0% in the corpus for each sentence in the corpus, right? That means each row or each list in the corpus, whatever you want to say. If I in send the split, then count equal count plus 1, and IDF dictionary we are maintaining. This is a dictionary. So from vocabulary, we will take one word and we calculate this value and we will insert. Okay. So we have defined this function. Okay, it will return us this IDF dictionary. Okay, so let's see. Let's call this function with corpus and vocab. Yeah, you can see here what are the inverse document frequency for each of the term in the vocabulary. It is printed here. Okay. Next is TF IDF. The most most popularly used thing. So it is nothing but multiply or multiplication between TF and IDF, and the result is called as TF IDF. Okay, so this result I need to print here. Okay. Okay, so this is the TF IDF of different terms in your vocabulary. All right. Now, this is part of basically word embedding, which is called what? Bag of word. Okay, so we have tried to do a kind of bag of word here manually. Okay, but let's see what result we get if we use the bag of word inbuilt functions in the Python. Okay, so see, for vocabulary list, we are doing the same thing here. Yeah, we are doing the same thing here first. Okay. Next. Okay. We are taking vocab list and initialize it to vocab list. We are sending tokens to this vocab list function, right? Then print vocabs. It will print the vocabulary what is created by it. Okay. So you just if you just want to try it out of it to get a clear view that what it is going to do for you. Okay. Okay, sorry. This. Okay, so I have sent here tokens, but I don't have, right. I should send. I have what in this vocab list. What we are printing here, I have not stored it here. Sorry, vocab Sorry. Okay, so we have vocab list. I have already shown you, right? Vocab list is my function what I had written. So it is that output. Okay, so I have already shown you. So this print is not needed here because I have already demonstrated this function. Okay, then we are taking a vector variable, which is a list type variable, right? For t in tokens, for that means for each token, what you are doing, we are printing the token first. Then we are again, reinitializing a new vector here. Then for w in vocab, right? Vector dot append t dot count w. Okay, and then this vector is going to be again appended with vectors. Okay, so you can see this is vectors and this is vector. Okay, these are not same. Understand? So it will become a list of list again. Okay, so vectorization is a function we have created. Okay. Okay. Next, what we can do here? Yeah. Vectorized. List object is not callable. Vector list tokens. Vector list. Is equal to vectorized preprocessed. Preprocessed coming says token here. Then vocab list. I'm sending here tokens. Right. Here I'm sending preprocessed. It is giving vocab list. Okay, it is getting, maybe it is getting confused between these variable names. Okay, so if I just run this first, okay, then if I run it here, yeah, so basically due to this collision of variable name, this error was coming. Okay, so you can see it is vectorized. Okay, and it is representing the whole sentence. Okay, you can see 1 1 1 here, but in the original sentence there was 6. No, not original sentence. In your vocabulary there is basically 6 words. You can see 1 2 3 4 5 6. So length of each vector become 6, and after that it is doing simply an present absent thing by doing it. Okay, so this is what the concept of bag of word. Okay, now you create the same thing using sklar. Okay, what we are going to do, we import pandas, then from sklar count vectorizer and type id vectorizer we are calling, then count vec equal to this type id vectorizer. In this we need to send the n-gram, basically n-gram range. So we are thinking about just one word at a time. So we are passing 1, 1. But if we are want to generate bag of word for bigram, you can send 2, 2 also. Okay, stop words also we need to send. So we are sending English stop words you need to use. Okay, then there is a transform function, count data, so count vec dot feed transform corpus. Okay, so this is one part basically. Another part is CV underscore data frame. The PD data frame, it is used for creating a new data frame, right? So count data, so this count data to array. So convert this to array. Okay, then another columns equal to what? Count vec dot get feature names. So understand. So you are just here by doing this, you are creating a data frame whose column names will be these terms in the vocabulary, and column values will come from this count data. All right. So if I run this, yeah, you can see this is the data frame is created, which is you can say bag of word. Okay, it have 1, 2, 3, 4, 5, 6. Yeah, the interesting thing is that still we have 6 vocabulary, and when we had done the same thing manually, we had done 6 value 6 terms in our vocabulary. Understand? So the same thing happened, and you can see here the sequence is not maintained. So they are basically in the background they are using the set function. So sequence is not maintained. But in our case, if you see, sequence is maintained here. All right. So based on the situation, you can choose. Okay. Then instead of giving time behind too many things, just in short, I'm just not going to explain much on this. Okay. So this is what this TF IDF you can calculate by using this inbuilt function. So okay, so let me do it step by step so that you can understand. No need. Okay, so you can see here with smooth, there is 2 options of using this TF IDF vectorizer. Okay, one way is you use smoothing, another way you can just not use the smoothing function. Okay, so TF IDF vec equal to TF, simply I'm calling this TF IDF vectorizer from sklearn Fisher extraction dot text. Okay, so this is I'm calling you used IDF is true. Use IDF, sorry, smooth the IDF. No, we don't want to smooth the values. Then in gram range, we want 1 gram only, and not using 2 grams or any other. Then stop word is English. These are the parameters we need to simply pass. Okay, then your vectorizer will be ready. Now, your vectorizer's name is TF-IDF vec. Okay, now TF-IDF data, because now we do the transformation. So TF-IDF data equal to TF-IDF vec dot fit transform. What was your original corpus? You pass. Okay, and then what will happen? This will have only raw values. So this is, you can say, simple array which does not have the column names. So we need to add the column names. Okay, so how we can add it? So we are creating a data frame in pandas. PD, PD is panda. Okay, so panda data frame we are creating. Values are simply this TF IDF data to array. So it is simply give a array of values. Okay, and columns we are writing here TF IDF vec dot get feature names. Okay, so it will feature names are basically the vocabulary or words available. Okay, so that will come here as a column names, and then it will be printed. With smooth, the same thing. You can see this smooth IDF is true. We made it true, so it will just smooth the values of IDF before using it in the TF IDF vectorizer. Okay, and with smoothing we will see how the values are changing. If you see here, for long, for the 0 means the fast review. Okay, for long you have this value. This is the TF IDF value. Okay, but for smoothing, this is the value we are getting. Okay, when you are using smoothing of what IDF. Okay, when you are smoothing the IDF, this value is, you can see, little low. Okay, so but in case of movie, it is higher. Okay, in case no, it is again yeah, it is low. Okay, in case of movie, with smoothing it is low. Without smoothing it is high. Okay, so you can understand we can do the same thing by using the inbuilt functions. Okay, so this is the part I had to discuss about this work to vec thing. Next, I will go for the word embedding part. Okay, so for word embedding, I will mainly use this Gutenberg what is called data set. Okay, just a minute. So you know that many times throughout our discussion you are listening about word embedding, right? Embedding techniques in NLP. So why do we need it, and what is this basically? The thing is very simple, that we need to assign similar values to the similar word. The same word, if it is same word, then it must have same values. But if they are similar word, they must have similar value, right? Because the machine learning model, deep learning model, all these things don't take this thing as input. That means text as input. Okay, all the models, they need to calculate some level of calculation. So for doing calculation, it needs numerical input on it. So we need to represent our document or sentence or whatever you want to say, your tokens or words into form of into numeric form. Okay, or in form of number. Okay, so another thing is happens here, that is contextual word embedding and static word embedding. So okay, yeah. So in contextual word embedding, aim at capturing the word semantic in different contexts to address the issue of polysemous and context-dependent nature of word. Okay, so I'm not going much detail in theory. Okay, so word embedding, there are some very popular embedding techniques. One of them is word to vec. And then, sorry. Okay, so one of them is word to vec. Then GLOVE is another model, the global vector for word representation. Then there is ELMO model also. Okay, so there is a lot many. This is endless list you can have. So these are something, some of the popular and basic, I can say. And our discussion will be based on this, what to make. Okay, so why do we need what to make? Basically, it can capture the semantic. Okay, so there is two kind of word to make model, in the same package in LTK. One is called continuous bag of word, and another is called skipgram. So if you have a good amount of data, then continuous bag of word will work very good. If you have a small amount of data, then usually it is recommended that people like to use skipgram. And the main difference is there, that is when you are using this continuous bag of word, what happens? You give n number of words as input, it gives you output another word which is related to these input words. Understand? So you give an incomplete sentence, say what one particular word is missing, it can recommend you or give you one missing word, like that. Okay, but in case of skipgram, there is another model of what to make. We give one input, okay, and it does all the calculation, and it, as output, it gives you multiple related word to the input word. Understand? So this happens. So like yeah, here you can say we have two sentences: have a good day and have a great day, right? So here you can understand that good and great here in the used in similar context, and their meaning is also almost similar here, right? So this is the first thing to note. Then vocabulary, if you see here, have, a, good, then great, and day. So how many? What is the size of your vocabulary is becoming? It is becoming 5. Now, how will you give this vocabulary as an input to your machine learning models or deep learning models or neural networks? So many of you, or somebody can say that we can do some one-hot encoding. That means what is one-hot encoding? That is, if there is 5 values or 5 candidate, you have to have 5 binary bits, and 1 bit will be on to represent each of the term in the vocabulary. Okay, so that is what happened here. You can see the diagonally have means have at the first position in your vocabulary. So 1 put it here, A is at the second position. So for A, 1 is put it here, and so on. So this is kind of this is called what one-hot encoding. But problem with this is that if you want to represent this first sentence using this one-hot encoding, what will happen? You will have 1, 2, 3, 4, 4 of such kind of string, and which will give you 4 into 5, then 20 features, right? So this is basically not an efficient thing, and it also does not do good in case of maintaining, you can say, in case of maintaining the similarity of a word, because you can understand for good, okay, maintaining the context of the word, but it definitely, if luckily, if you have this kind of thing, your codes for different word, similar word, you may get similar, but it is based on luck. Only if you do simply one-hot encoding. Okay, so you can see here for good, the vector is 0, 0, 1, 0, 0. For great, 0, 0, 1, 0. Okay, so you can understand this, right? So better option we need to find, that is called what? And that is the what to take is one of the good option for this. Now there are definitely some pre-trained models. I'm not going into that, so let's jump to the what to bake implementation. As we don't have much time, I have some code. I'm just copying them and pasting here and explaining to you. Okay, so that is it. Okay, so for implementing it, first of all, we have to implement, we have to import some of the libraries, right? So like pandas, we already familiar with. Word tokenize, we already familiar with. Word to make, which is belongs to GenSim module of Python, and NumPy also we are importing as NP. Okay, so let's import them. Then okay, then we are just going to import our data set. Here our data set is a book. Okay, the detail of the book I will show you. You just if you just copy this link and TXT, right? Text. Okay. So this book is the Project Gutenberg ebook of Alice's Adventure in the Wonderland by Lewis Carroll. Okay. So you can see this is a whole book. Okay. And the title I have shown you. Right. So this book I'm just taking from this URL for our work. Okay. So how we can get access to this? We have to import first NLTK.data. Okay. Then sentence tokenizer we will need, because this book, if you see, it is in continuous document. So we have to split this document, this huge text into small sentences, right? So we will need this send tokenize. Okay, then we will download Punkt. We know why, previously also I have shown you. Okay, then URL library we have to import. Okay, from where we will import request, because we are requesting some URL and we are just you can say picking up the text from there. Okay, so this is what we have done till now. Sorry. Okay, then if you just want to see, what thing we got by importing it. Okay, so okay, first let you open the file. Okay, so see, this is a variable where we had put the URL of the file. Okay, now request.url open. Now we are opening the URL into response Alice variable. Okay, then reading the file. Here is something you people was asking in previous day. That is recording, encoding, and decoding. Now see, as if you see in the text, there will be many characters which are not in ASCII format or in UTF-8 format. Okay, so what we are doing here, even this kind of double quotes, if you see, they may not be in UTF format. Okay, and there may be some other many symbols. Okay, so I'm not searching. It is not possible. Yeah. So okay, just we are doing the decoding here itself, so that the raw text, what we are getting out of it, it is all the characters are in UTF-8 format, and we will not get this kind of exception or error later on. Okay, then we split in sentences. Okay, so tokenize Alice, we are doing a sent tokenize. Okay, so we are passing this through raw data. Okay, now how many sentences we have got by doing this? Just do this, understand? We had 1102 sentences here, right? In the document. Okay, then remove content means what we are doing. You can see tokenize Alice equal tokenize Alice, but we are just considering the 14th word onwards up to end. Why? Because at the beginning, if you see this, there some of these things are there, right? So we would just like to not take these text into our consideration or into our analysis. So we can do this. Okay, so this is the thing we're doing. Then if I just print the raw alias, if you see, you will understand. See, at the beginning, this project, Gutenberg ebook, and all these things are there. We don't want this. Instead, if I print this, tokenized Alice, you can see, oh my God, it's just filled up. So it will take time. So I'm just let's try this. So this is the 10th sentence. If you want to see the first sentence, you will see. Okay, so this is the first sentence into this. Okay. Okay, so let's move. Now we have the sentences. We can now split them into word, or we can tokenize them, right? So we do this. So you can see we are just taking word tokenize here, right? Then in the row Alice, we are replacing all the new lines available there. Okay, so this is simply just to ignore the warnings. This part is done, so don't think about this part. Okay, so in the basically we are again using the raw Alice, not the tokenized thing. Okay, so from the raw Alice, all the new lines we have removed first. Okay, then we had written this tokenization function, so I am not going to explain it again. Okay, then we had written this remove stop word function, put it here. We had already written this. Okay, let's go with just modifying this or calling these functions also. Okay, so that you can understand that what is happening in each of the part. Okay, so tokenization function, we are calling it here. Let's see. Okay, so the raw Alice is basically here tokenized. Okay, the raw Alice is tokenized here. Okay, then remove stop word. Okay, so we know this thing we have to do. Basically, the stop word need to be downloaded and all we have done. Then we take this function we had previously written. Okay, then we will call the function. Okay, so stop words are being can say removed. Then we are going for removing the punctuations. This function also our one function what we had written in the previous session. Okay, so doing this. So after removing punctuation, let's see how our tokens are looking like. You can see this is how it is looking like. Then yeah, this is a new function. We're just removing all the non-alphabets. Okay, because there is many this slash, sometimes this semicolon, and all these things are there in our token double quote. Okay, so we just want to remove them from our text. Okay, so do this. So it is just using is alpha function we are doing. Okay, I'm just not going into each line's explanation. Reason is you are already becoming habituated with Python a little bit, and we don't have much time. So I'm trying to just cover it as soon as possible. Now we are creating the model of what do bake. So what do bake we had called at the beginning. I think you remember from the GenSim library. Okay, so the model is created. So here I have listed what are the different parameter you can pass to it. Okay, so token you must definitely you have to pass, right? Then minimum count. So here we have put it to 1, but by default it is 5. Okay, then size size of the vector basically we have limited. Sorry, we have put it We have put it at 100. By default, it is also 100. Okay, but there are other things also. This SZ you can set to use the skipgram or CBOW or continuous backup word, which model you are trying to use. Okay, by default it will be COP only. Okay. An number of iteration you want to iterate, all these things. Basically, you have to understand one thing here. This word to bake is nothing but a neural network. Okay, it is a neural networking. Actually, this neural network, thinks that how each token will be assigned with some vector. Understand? Now see how this model is working. Okay. So first, let's print the model. It is that in the vocabulary of your model, there is 2731 vocabulary, size is 100, and alpha value is 0.025. Okay, alpha is what? Learning rate. If you know the neural networks, this learning rate is there. So alpha is there, learning rate, what they have used. Okay, next you just come here. Okay, if I just the learned vocabulary of tokens is stored into this place. Okay, this, and after learning, what vocabulary is generated, that is going to be stored into this place, that is model.wv. Okay, so if you see here what we are doing, we are just taking 10 of the token into our we are just trying to print 10 of the tokens here, because this model.mv is not a simple list. Okay, so you can't print it by using a simple print command and giving some slice. Okay, so using for loop we are printing it. Okay, so you can see all these are the part of vocabulary. That means this 2731 words. Okay, next you go do some more exploration on this. Okay, so what you go, some words we are taking out of it. Yeah, so what are the words that there in the vocabulary? Okay, so that time we had done it using what? Using a for loop. Now we are simply taken all out, so you can see the list of words and came in the present in the vocabulary, right? So next you go length of this this thing was already we have seen in the detail of the model when we had printed, but manually again we can check it. Okay, this is the size of the vocabulary. Okay, now something what we was speaking about, let's do that. See, we want to see what is the vector generated for the term Alice. Okay, sorry, length of the vector for Alice. You can see here it is 100. Okay, but if you want to see what is the actual vector for Alice, you can just print the vector. Okay, or you can just you can see, you can do this. Okay, the first one is printing the vector for drink. Okay, so drink is a word in the vocabulary. You can see here, this is the vector. Okay, for drink, and for Alice, this is the vector. Okay, so in this vector, basically there is 100 such terms or such numbers. Okay, so this is what you can say vector form of each word. Okay, this is what our what to bake have done. It converted a word to a vector of size 100. Simply said. Okay, now you go do some more exploration, like we are taking input say Alice, and we want to see what is the most positive and similar word available in the vocabulary to the Alice, right? Now, thing is that here similarity means what? Most related. Okay, so you see here, see, said, little, queen, one, went. So these are the different words, frequently appeared with Alice. You can see here the score is also given. Okay, see 9.8. This is the similarity score, you can say. Okay, cosine similarity. All right. So this is the similarity. So this is how, for the similar word, it gives similar score. So as these words are more very related to Alice, okay, and frequently appeared with Alice, you can see all these words are having quite similar distance from Alice. Okay, then take two words and just based on that, you take the distance of the third word. Okay, say Alice and said we have Kate. Okay, and in W2 we have Wonderland. Okay, so what is the what is the related word among, you can say this this is positive and negative is W2. You can understand that this Alice, when Alice is positive and this second word is negative. Okay, so how many times it can, or you can say what is the top two words due to which this happens or related to this. Okay, so that is one, and another word is there, that is cloud. That means it maybe there somewhere it is written when due to cloud Alice was not entered into Wonderland or something like that, maybe there. Okay, so due to this words, basically this and this word pair became negative, I think. Okay, so this is what we can do. Okay, sorry, most similar. Then yeah, odd thing out. This is another interesting thing you can see here. See, Alice, went, and Queen we have given together. See, went is odd here. Alice and Queen, they are quite similar. Okay, so in this way you can choose any number of words from our vocabulary here. Okay, and you can just pass to this, and your model will based on the distance among these words, it will say which are most related and which word is at the longest distance among all to all other available words or terms. Okay, so this is the final code I'm just going to put here. Okay, this is you can see we're using CB, that is continuous bag of word model. Okay, and you can see this is the result we are getting. Similarity between Alice and Wonderland is this and this. Okay, so by default it is using CBOW, and if you use skipgram for the same database, what kind of result you will find? As I told you, there's two kind of thing in here. So as you can see, SG equal to 1 is set to select skipgram, and you can see the similarity, cosine similarity between Alice and Wonderland and skipgram is very high. Okay, but when you are using continuous backup word, they are very low. So you can understand, based on your situation and context, you have to choose the model, whether you will use the skipgram or whether you will use the continuous backup word. Okay, so this is all from my side for today. It is already time for your quiz. So I'm just ending this here. If you have some question, just a minute. You can ask some question in a very fast manner.
Please share this notebook to us.
Yeah, sure. In GitHub, I will share it, okay? And I'll share the link, all right?
Sir, can this method be followed for Indian languages also?
Excuse me, your voice was too low.
Sir, am I audible?
Yes, you are audible.
Sir, can this method be used for Indian languages also?
The same question. You have to check out, okay? I have never checked because I had not worked, with Indian language in past. But we need to check it.
Okay, sir.
Okay. But I have shown the things manually, right? You got the concept, I think, how this code can be written, right?
How this Alan and that machine word is related? It is showing means in the next model it is showing similarity. Similarity means meaning of similarities if two words are nearer or nearer in the
Here
meaning.
the
It is not
similarity
showing.
means here the similarity means how frequently they are, appearing or occurring together. What I understand. Here similarity does not mean synonyms.
Yes. Yes,
Okay.
nearer word we can say.
Yeah. What
Distance
this is what
less.
machine understand. This is not a human understanding.
Distance can be the.
JP sir, are you there? JP sir?
Bhaskar sir?
Sir,
Yeah,
form
yeah.
is opening. Form is not opening till now.
Sir, could you please share both the files with us because I'm unable to download this file from your GitHub?
From GitHub, I'm telling you how to download. You just go to my NLP folder. Two link I had shared. You go to
Sir,
the first link.
can you share on the
Okay,
Google
then
Doc?
you
So this file
download.
link also you share, sir, Gutenberg's file?
Yeah, definitely, I will. Okay, Gutenberg, this link, text file link. So it is already there in the notebook. I am sharing it in 30 minutes. Okay.
Okay, sir.
Don't worry. Yeah.
Excuse me,
So
sir.
let's go for your, yeah.
Sir, I'm asking about the quiz that you have tried to post it on 7.
It's not
Yes,
opening.
yes, yes.
Not able to.
It will not open now. We are in a discussion how it can be open.
Okay. Okay.
You just don't worry, okay?
Okay. Fine.
Yeah. So I am opening it at 50, and I will give extra this 5 minutes. Okay.
Okay. Sir, Bhaskar sir.
Yes,
Sir,
yes.
it would be appreciated if you could just make the course material available like right after the class every day. I mean, some of us are just starting out in the field, unlike some
I
people who
understand.
already, yeah.
See,
So
when
that
it
would be.
is taken by our NIT people, NIT Patna people, then it is not a big issue. But when it is some professor from other institute, then it depends when they are providing us. Understand? That time it is no more in our hand.
At least, sir,
Okay,
recordings can be given. Recordings, because that gets automatically
recording we are
generated.
sharing again today. Also, JP sir will share. Don't worry about that. We
The
had
previous
shared.
recordings
Okay,
are
sir.
not
Thank
in
you.
that same folder which you had given on the first day. On first day, there one folder is given for FDP 2022. The name of that
Okay.
folder.
In that one, okay, I will put that in that one also.
Because that becomes a single point of contact for everything at
I
one.
understand. Yes. Okay, sure. So you all have the link, right?
In Google.
I'm just opening the form because it is already 49. So I have activated the form. You can log in. Okay. You can log in and you can start giving the exam. Okay. The exam will end at 8:10 p.m. I posted the link here also in the chat box. I'm ending the meeting here, okay? We don't need the meeting.